The estimation of duration in fixed income and in bond pricing is a relatively significant topic because duration is taken as a measure of the degree to which the changes in the bond price occur as a result of changes in the interest rate. So relatively, one theoretical interpretation of the duration follows these lines, that the change in the bond price divided by the original bond price is equal to a negative duration measure times the change in the interest rate, where y here denotes the discount rate or the interest rate. So if we want to get some kind of summary measure or proxy measure for the sensitivity of a bond to changes in interest rates, we look to duration. Interestingly, it's quite common in finance that we discount bonds using continuous rates as opposed to discrete rates. When we apply a continuous rate, the way we estimate duration changes slightly. So we just take a look at a few worked examples and then illustrate a little bit also with C++ code some implementation of these estimates. So basically the setup here is we want to know the duration of a 10% coupon bond where the face value of the bond is 100. The yield, in other words the discount rate, is 8%, and we're using a continuously compounded rate. The coupon is paid semi-annually, so it's not once a year but twice a year the coupon is paid, and we have to adjust this 10% to reflect that, and the bond has a maturity of 3 years. So the basic implementation then is we take the 10%, the coupon rate, we multiply by the face, 100, that gives us 10, and then we take, because it's a semi-annual bond, we divide that $10 by 2, we get 5. So every 6 months, month 6, month 12, month 18, month 24, month 30, month 36, every 6 months we're applying a coupon not of 10 but half of 10, which is the 5, and then we discount at the relevant discount rate, which in this instance here is the yield of 8%, and that doesn't have to be adjusted. That can be read directly in as 8%, and just we take the product of the discount rate and the period when a coupon is paid, and so we have 6 monthly intervals that accumulate up to the 3 years. The 3 years here represents maturity. Note that at maturity, in addition to the coupon being paid, the 5, we also get the face value of the bond redeemed at. So a small implementation then of that in C++ I have already set up, so we might just take at that, and what we have here is basically a relatively simple parsimonious program, whereas before, we just take the bond details. There's a face value 100, if you recall. The coupon rate in our particular question was 10%. We had to divide that by 2 given the periodicity of the semi-annual, but the coupon rate was equal to 10%. The discount rate was equal to, go back and check, the discount rate was equal to the 8%. The face value was equal to 100, recall. The periodicity of the coupon payment was twice a year, semi-annual, so M was equal to 2 and T was equal to 3. Okay, so those are the values consistent with the worked example that we've looked at. The way I estimate the bond here is I use a loop to read in the coupons. The coupon payments are estimated as being equivalent to the coupon rate divided by M, which was the 2, and then we multiply that by the face. So the 10% divided by 2 is 5, and the 5% of 100 is 5. So the coupon each period every 6 months is going to be 5. Then we set out a loop where we run through the loop. We've declared already a double variable b. that BV represents kind of a bucket where we initialize it or seed it as a value of 0. At each stage of the running through the loop, as we the loop is a series of 6, a series of t is equal to 3, m is equal to 2, so we have 6 runs through the loop. So m by t is 6, and I is 1, 2, 3, 4, 5, 6. So we initialize I at 1. It'll keep adding to be 1, 2, 3, 4, 5, 6. And each time we run through the loop, we discount. We take the coupon, which is 5. We discount it at the discount rate of 8%. The discount rate then is multiplied by the 1, 2, 3, 4, 5, 6. But remember, when the coupon is occurring at 6 months, so we take half of 1 is 0.5, half of 2, which is 1, and so we go up in steps of half, and that's engineered here by taking the I, dividing it by 2. So we go 0.5, 1, 1.5, 2, 2.5, 3, and once we hit 3, which is 3 by 2 is 6. Once we hit that 6 here, then we exit the loop. We take whatever value, residual value is in BV, and then we add on to that BV the discounted face. So the face value is 100. We discount using the exponential term, and we're discounting the 100, which then gets added into the BV. And the BV then represents, if you like, when we return the BV, we are returning the present value of the bond. We can observe here that the value is 104.80. We might check against another example. Okay, that's the example here. Let's take another example where the bond price is different. It's going to be 110.57. So if let's see, do I have a worked example perhaps? Okay, let's take this one. Coupon 14%, face 100, continuous dividend, the discount rate continuously compounded 12%, and it's semi-annual over a 3-year period. Okay, so if we remove that to one side and just bring down here for a moment, we can adjust our numbers to reflect. Okay, so we bring this to one side, and then we can take this here, bring up our, okay, and so what we have here is, okay, so we don't change the 100, it remains the same, but we change the coupon rate to 14. So the coupon rate goes to 14. The time period is not changed, it's also 3 years, so that's the same. It's a semi-annual bond, so it's 2. The discount rate is equal to 12%, so we reflect that in 12%, 1, 2, and then we can run this. And while we're running, we can compare the results we get. So what we should get in terms of the present value of the bond should be this 103.99.1, which is the case. So it looks as if this formula here is this C++ code manages to execute and correctly estimates the value of a bond, which is derived from continuously taking a continuous rate and discounting the coupons and discounting the face.